In this video, I'm going to demonstrate three types of collisions: elastic, inelastic, and completely inelastic, also known as a perfectly inelastic collision, as well as an explosion. So let's talk about elastic versus inelastic. Elastic collisions only occur between atoms and molecules, so energy is not lost. In an inelastic collision, energy is lost due to the deformation of the objects during a collision. In elastic and inelastic, the objects will bounce off one another. So here is one object, here's another object. They are of equal mass, so this one could be stationary, that can move, it bounces off. Or I have two objects collide and they bounce off of one another. That would be an example of inelastic as well as elastic. A completely inelastic collision, also known as a perfect collision, is a collision in which the objects stick together, hence the term perfect. It's a perfect unification of the two objects. So I'm going to use the carts again. And so let's have this cart here stationary, and this one will come and it'll collide with it, and that makes that a perfectly inelastic collision. Now we can take another cart that has this little plunger right here, and in an explosion we have a system. Here I have a system that obviously has two parts, and what's going to happen is I'm going to just press this button here, and the two objects explode and they split apart. So that summarizes the three collisions plus the explosion. We don't call the explosion a separate type of collision because really an explosion is the opposite of a completely inelastic collision. In a completely inelastic collisions, objects combine to form one system, and in an explosion you have one system that splits into two. So here are a couple of examples that I want to review. So let's begin with taking two objects of equal mass. So we have a cart here, and we have another cart here. These two have the same mass. They happen to be 500 grams. And object 2 right here is going to remain stationary, and object 1 will collide into it. And what we see is that object 1 becomes stationary and object 2 starts to move. And because the two masses are the same, what ends up happening is the initial velocity of object 1 is going to be equal to the final velocity of object 2, and object 1 stops moving. Now, if we repeat that collision, but we make object 1 more massive, so now I've doubled the mass by adding this weight here. So this will be stationary. And let's see what happens when the two collide. So we see that both objects end up having a final velocity. The final velocity of object 2, the one that was initially stationary, is greater than the initial velocity of object 1. And another thing is object 1 does not come to a stop upon collision, so it retains some of its initial momentum. Of course, that all depends on the relative masses of the two objects, so you can calculate that if you know some of the numbers. These are the final two examples. So let's take the two objects, and we have to make sure that the two objects are both stationary. So here's one object, and we're going to have a second object right here. So we saw this before. And what I'm going to do here is, so the system right here has no momentum. There's no momentum in object 1, no momentum in object 2. And what I'm going to do is I'm going to push the button, cause them to explode, and they move away from one another. And the fact that they move away from one another tells us that their velocities are in opposite directions. And because the two masses were the same, the two speeds are the same, but the velocity, of course, includes direction. So the speed of one object is left, and the speed of object number 2 is towards the right. So opposite direction for their speeds. Now what happens if we make object 2 more massive? Well, let's double its mass. Push in the plunger and set that off, and let's see what will happen this time. So let's press the button. And what we see here is initially we have no momentum, and in the end the speed of this object is towards the left, the speed of that object is towards the right. But you notice that the lighter object moves faster than the more massive object. Now, I just want to end with this idea is in these two examples, you notice that initially the momentum is equal to 0. So that means that the total momentum after collision also has to equal to 0. And the way that happens is if you notice that the momentum here is based on a positive velocity and the momentum here is based on a negative velocity. So the two momenta will end up canceling each other out. So the sum of the momentum is 0 before and after the collision.